Let's look at some examples of using interval notation and graphing solutions to inequalities. So to start with, let's start with an inequality and then graph the solutions to that inequality and write the corresponding interval using interval notation. So I'm talking about something like, say, this inequality, x greater than 2, say, something like this. This is the sort of thing you might end up with if you have a more complicated inequality and then you solve it for x. You might end up with something like this. So one nice way to come up with or to understand how to graph this sort of thing is just to read this out loud. This says that x is greater than 2. X is the numbers that we want. So another way to read this is we want numbers greater than 2. So on the number line, where do those live? Well, all of the numbers greater than 2 are over here. They're numbers larger than 2 are to the right of 2. So that's how to graph the collection of solutions to this kind of inequality. Now, one thing that we haven't really indicated so far is 2 itself one of the numbers that is a solution to this inequality. The graph doesn't really tell you clearly whether it is or not. Well, for this inequality, 2 is not a solution because if you put 2 in here for x, you get the statement 2 greater than 2. But 2 is not greater than 2. It's equal to 2. So 2 is not a solution to this inequality. So on the graph, we need to have some way to clearly indicate that although every number greater than 2 is a solution, 2 itself is not a solution. And the way to do that is there's sort of two ways. One is draw an open circle around 2. The openness of the circle is supposed to somehow indicate that although the shaded area on the graph gets really close to 2, it doesn't actually land on 2 itself. There's sort of a gap at 2. The other way that some people use to indicate that 2 itself is not a solution is, so here let me shade everything to the right of 2 again. They use a round bracket. Somehow the round bracket or parenthesis is supposed to give you the feeling that you're approaching 2 but not quite touching 2. Now for interval notation, remember the way interval notation works is you write down the left endpoint of your interval, comma, the right endpoint of your interval, and then you use either parentheses or square brackets depending on whether that endpoint is included or not. So our interval starts at 2 on the left. To the right, it goes on forever, and that means it goes to positive infinity, right? Way out here is positive infinity beyond all of the finite numbers, so positive infinity here. All right, and now we need to indicate for each endpoint, is that endpoint included or not? So for the right endpoint, infinity, infinity is never included because what we're trying to write is the collection of real numbers that are solutions to this inequality. But infinity isn't a real number, so we will always exclude infinity. And to indicate that this endpoint is not part of our interval, we will use a parenthesis, a round bracket. All right, now for the left-hand endpoint, is 2 part of our interval? It's not. We noticed that earlier, so we need to use a round bracket, a parenthesis, on the left as well. So there's the interval notation, there's the graph, and here's the inequality that it came from. Let's look at another example. How about something like x less than or equal to 7? All right, so we need a number line. We need to put 7 on here somewhere, so let's put it right here. Now this time x, which again is representing the numbers that we're trying to describe, so the numbers we care about are less than or equal to 7. Numbers that are less than 7 are to the left of 7, so that's all of these guys over here. And now we need to indicate that 7 actually is a solution to this inequality, right? Because this inequality says less than or equal to. So since equal is allowed, 7 is okay in here for x, right? 7 less than or equal to 7, that's a true statement because 7 is equal to 7. So we need to indicate on this graph that 7 is part of our collection of solutions. So if it weren't, we would use an open circle. Since it is, we'll use a closed circle, a filled-in dot like this. And if you prefer the bracket notation on your number lines, so here's 7, everything to the left of 7. If you prefer bracket notation, you'd use a square bracket like this. So these are the two ways of indicating that this endpoint is part of the collection of solutions. All right, now let's write interval notation. So the left end of this interval, well, it goes all the way down to negative infinity all the way on the left. So negative infinity is our left-hand endpoint, and our right-hand endpoint is 7. And now again, we need to indicate for each endpoint, is that endpoint included or not? Well, negative infinity, again, it's not a real number, and so we can't include it, so we use a round bracket. But 7 is included. 7 is part of this collection of solutions. So to indicate that using interval notation, we use a square bracket. Okay, so it's a little bit strange to see brackets or parentheses that don't match, but that's just sort of an artifact of how we use interval notation, right? We have to indicate for each endpoint separately, is that endpoint included or not? Since we have one endpoint that isn't included and one endpoint that is included, we get one square bracket and one round bracket, which is a little funny looking, but that is the way interval notation works.